Good morning, everyone. This is Nikki. I'm the Director of Research Strategy and Programs for the Renewable Thermal Alliance. I know we have a few participants today and we're going to get started. We will make this recording available after the fact. So if you are looking to take notes or access the information again, that will be made available on our Basecamp site. I'm really personally very excited to have everybody here with us today and introduce Jordan Kearns, CEO of Medley Thermal. Jordan had recently participated in the Innovation Day sponsored by Avangrid in Orange, Connecticut, and had connected with Stuart DeCue, the Executive Director of the Yale Center for Business and the Environment, which is the entity at Yale that sits between the School of Forestry and Environmental Studies and the School of Management and is the home to the RTA. We're really excited for Jordan to share a little bit about his company and his background and the types of innovations that Medley Thermal is working on. If you have any questions or comments, feel free to use the chat function that you should see at the bottom of your screen. And we will kind of keep track of those. Jordan has left some time at the end for questions and discussion. And certainly if you're having any technical issues or you're not able to hear or see anything, let us know so that we can fix those as quickly as possible. Jordan, I will turn it over to you, and I'm going to mute my side just to keep the sound quality running.
All right. Thanks so much, Nikki, for that introduction. And yes, so I think there's a Q&A button at the bottom, and I believe you can take the questions through that rather than through the chat. Is that correct, Nikki?
Yes, so feel free to direct. We can either use the chat function or the Q&A, however you feel most comfortable facilitating that.
Yeah, I think Q&A would be fine. I have that screen up here, so I'll be sure to see that. I might miss the chat. All right. So yeah, thank you, Nikki, so much for that introduction. As Nikki mentioned, I'm the founder and CEO of Medley Thermal, and our company was founded on a simple idea, which is linking clean, cheap power to thermal systems. In other words, use electricity at times when it's available cheaply and cleanly because of surging renewable production, and use that electricity to heat stuff up and offset the fossil fuels that we would otherwise burn to do the same job. So before I get into our company, I kind of want to divide the webinar into two parts. And for the first part, I want to talk briefly about how electricity economics are changing and how electricity markets are developing and how that's opening up new opportunities for electrification, like the opportunities that we're trying to take advantage of as a company. And then I'll talk a bit about our company in specific, our current work, and our ongoing demonstration project in upstate New York. So to begin with, I want to take you to early morning in upstate New York. This is the Maple Ridge Wind Farm, and at 320 megawatts of capacity, it's the largest wind farm in the Northeast. Right now, you can imagine the sun is just coming up over the horizon and the wind is blowing very strong. So this wind turbine is outputting, or this wind farm is outputting at its maximum capacity of 320 megawatts. This should be the best time for a wind farm to be selling its power, but the price of power right now is next to nothing. And often we find in places like upstate New York, the prices can hit very, very low, just tens of $10 a megawatt hour, even zero, sometimes even negative. And this is not an anomaly. In fact, compared to average prices in the state of New York, wind power produces at times and locations where it sells at about a 33% discount to the average price of power in the state. This is happening because the wind doesn't blow exactly where and when we need it. The wind tends to blow strongest at night and early morning when power demand is low and prices are therefore lower. And the wind production also tends to be concentrated upstate in rural areas, whereas most of the demand is located downstate and in more urban areas. So this is a mismatch that we're going to continue to see as we continue to add more wind into rural areas. We're going to have more turbines being blown by wind at the same time in the same places. This is only going to deepen this discount because they'll be selling their power into the same already saturated markets. So wind in upstate New York has always sold at a discount to average power prices. What's really interesting to me is how this discount is going to change as we add more renewables to the grid. And I think solar in California is an excellent little mini case study on that. So solar energy, unlike wind, tends to produce in the middle of the day when energy demands and prices are highest. We can also co-locate solar with urban centers more directly, which also leads to a premium for its sale price. So for these reasons, historically, solar power used to always sell at a premium to the average price of power. In California, this is about a 10% premium as recently as 5 years ago. Since then, though, solar power prices, or the price perceived by a solar producer, has fallen 25% relative to average prices. And now solar sells at a 15% discount on average compared to just the average price of power for the state. This is the result of the infamous duck curve, but basically this is the result of just more power happening at the same times in the same locations, and supply and demand being mismatched. In fact, sometimes in California, the demand is so mismatched from solar supply that we hit pretty frequent periods of negative prices. In fact, the CEO of Calpine, a major California generation company headquartered in New York, testified last year that their most profitable project as a power generation company was actually running giant electric resistance heaters outside in the middle of the day to waste electricity as heat and take advantage of negatively priced power. We see this as a huge waste of a great renewable and clean resource. Ultimately, though, renewables have an even steeper problem. You don't have to be just cheaper than fossil fuel generation at this point. You also have to be able to account for the fact that your revenue is going to be increasingly declining over time because of this impact of seeing decreasing prices due to this crowding out effect. But even beyond the fact that renewable prices have been falling relative to averages, the difficulty for renewables is actually a little bit higher, because in addition to selling at a discount to average power prices as a whole have fallen over 50% over the past decade. So this is a graph from the major ISOs across the United States, and you can see that for a number of reasons over the past 10 to 15 years, power prices have been falling. This has been driven by the economic recession, stagnant electricity demand, growing amounts of renewable power, but predominantly falling natural gas prices. And what we see is across the country, steady amounts of decline. Now in ISO New England and New York, the regions that represent the Northeast, you have consistently higher electricity prices, but they have not been immune to this trend. So this is just New York, and you can see power prices 10 to 15 years ago were in the mid 90s, and now we're looking at $40 to $50 per megawatt hour of energy. And as we continue to add wind and solar to the grid, predictions say that the average price is going to continue to fall as well. So a recent study from Berkeley National Labs predicted that transitioning New York to a combination of 40% wind and solar would lead to an additional 40% decline in average power prices, with average wholesale prices of electricity being about 2.5 cents per kilowatt hour, and then renewable prices selling at a discount even to that, because they are also producing at these times and locations when power is less valuable than average. So what does this mean for the future of renewable electricity? If we want to see more wind farms like the Maple Ridge facility in upstate New York, we need a revenue pool for these facilities, or a market pool. Revenue has to be available for these facilities to be able to justify economically putting their generation on the grid. We have a $3 trillion asset base for our country's generation fleet, and turning that over is going to require some amount of market pool. I don't believe it can all be government push. Ultimately, there are three ways that we can create new revenues, in my mind, for renewable power. We can move it in time by storing it with battery technology. We can move it locationally by building out transmission and distribution infrastructure. Those two get the majority of the attention, but I think the third and a potentially very interesting use is to move the power to a new market, basically electrification, particularly of thermal loads. And I can guarantee that at the same time facilities like Maple Ridge are seeing very low prices for power, there are nearby facilities that are burning fossil fuels to generate heat. As I'm sure you all know, as members of the Renewable Thermal Alliance, that thermal energy is a huge part of our nation's energy use. So I apologize, this pie chart is not displaying correctly, but the orange segment is about 35% of US final energy use, and that represents thermal energy end uses. About the smaller blue segment is electricity, and the green segment, that's also about a third, represents transportation and mobility. And a lot of people have been focused on electrification of transportation, but electrification of thermal loads, I think, has gotten much less mainstream attention, and we see it as a natural fit. So annually, steam generation alone, a subset of that thermal market at large commercial and industrial facilities, costs about $50 billion a year worth of fossil fuels and emits 500 million tons of carbon dioxide, creating the steam used to meet thermal loads for large buildings, either to heat the space or for process steam to drive an industrial process. We see a natural pairing between this excess energy and thermal loads. I think a lot of times we think of us as a user or a beneficiary of renewable technologies, but really renewable technologies needs us. They need new markets to export their power, because right now they are really struggling with periods of low power prices, and predictions say that's only going to rise. So in 2017, I, with a few others, founded Medley Thermal with the goal of linking clean, cheap power to these thermal systems, basically taking this energy whenever it's available cleanly and cheaply and connecting it to off-takers who can add value to it by moving it into the thermal market. The way we do this is by dynamically electrifying steam systems. So this is a schematic of what we're looking at, but basically it's a hybrid boiler system that allows a facility to make use of electricity whenever power is available more cleanly and more cheaply than their status quo fuel source. To dynamically electrify a system, a new electric boiler is installed in parallel with the facility's existing fossil fuel boiler. And at times when power from the grid is cheaper, we switch over in a seamless fashion that does not disrupt the supply of steam to the end user. From a grid perspective, this is a great asset. The system is highly flexible and it's fully curtailable electric load. Additionally, since the fossil fuel system remains in place to back up the electric system, we can back off on our consumption of electricity whenever we are constraining either grid supply or grid networks. Ultimately, the system works like an ultra low-cost battery, except instead of shifting power in time, we shift it into this new market, the thermal space. The hardware behind this is also all mature and available at very low cost. So electric boilers have been around for over 50 years. They have a strong reliability record. They've been used primarily in places like Norway and Scandinavia, where you have already a just base load of very clean, very low cost electricity. So there's a lot of experience there, and these are already available from existing vendors at low costs, about $25,000 per megawatt at scale, which we see as a astonishingly low capital cost in the energy space. Because the electric boiler, which is the primary driver of the capital cost of a conversion, is available at such a low cost, we estimate that facilities adopting our solution in our initial target market will see about a 4-year payback period on average. Now, because the hardware is mature, our focus as a company is primarily on the optimization and dispatch of these systems. Our software enables effective operation of the hybrid system by synthesizing multiple data sources together to make intelligent decisions about when to buy electricity versus the status quo fuel source. So we consider real-time market prices as well as market forecasts. We're working on integrating real-time grid emissions so that we can incorporate that into the dispatch. We also look at the electricity tariffs as well as any fuel supply contracts and how that affects decisions that should be made, and then the technological constraints of the hybrid system. These are things such as the costs associated with cycling the boilers, the ramp rates, and the time to switch between the two. All of this is synthesized using optimization techniques and then sent out to the boiler system, and we also have a user interface to display that. So with our initial software solution in our initial target market of the Northeast, we can reduce energy costs by about 25% for certain customers, and greenhouse gas emissions from the boiler by about 25% as well. And I'll go into those numbers in a bit more detail later. So right now we're focusing, as I mentioned, on the Northeast as a market, specifically larger commercial and industrial facilities relying on delivered fuels such as oil and propane. This isn't the only place where we see our technology is applicable, but as an early stage company, we're interested in focusing on basically the lowest hanging fruit for our solution, the places where it makes the most sense to deploy, learn more there as an early stage company from early deployments, and then scale out beyond this initial market. We've selected this market for a few reasons that I want to go into, but in summary, this region has a high and growing amount of renewable penetration, particularly in certain areas. There's a progressive tariff structure, and obviously delivered fuels such as oil and propane are much more costly, which increase the benefits of dynamically electrifying. So as I mentioned, the Northeast has a growing base of renewables and zero carbon generation as a whole. So New York actually has about 60% already in the upstate region of zero carbon electricity. This is driven right now primarily by nuclear and hydropower, but obviously the state has very ambitious goals for adopting more wind and solar as well. So we expect this to grow from that base. New England overall is actually already 40% zero carbon, and certain pockets such as Maine are already about 80% zero carbon. And again, since we purchase at certain times when renewables are most productive, the times that we are consuming electricity, renewables such as hydro or biomass are often the marginal producer or the predominant source of electricity on the local grid. Progressive tariff structures, basically what we mean by this are electricity tariffs that seek to align the customer's energy costs with the utility's actual cost to serve. Historically, utilities would simply offer your electricity on a flat dollar per kilowatt hour rate, which doesn't really send the appropriate signals to the end user. As flexible load, we can respond to all sorts of signals which reduce the utility's costs, and a progressive tariff structure reflects that and allows the customer to capture some of those cost savings by being flexible load. So for the United States, the typical electricity cost breakdown looks like what I have here. Generation and capacity together make up about, this is your energy, that makes up about half of your bill. Another third is probably going to be the wires that bring the electricity to your facility, that's transmission and distribution. And then the remainder are taxes, which governments historically have put on electricity because your reaction to electricity, you're not going to consume less electricity. So it's a potentially a good way to raise revenue if you're a government. So as flexible load, we consume at times when renewables are predominant and costs are low. So actually just by consuming more intelligently, we can take advantage of variable generation prices and get a price for our generation that's about half the cost of average by consuming at the lower 50% of cost hours. Additionally, your capacity payments and your transmission and distribution payments are driven by your contribution to system peaks, either the local distribution system peak or the transmission peak. Capacity is basically the reserve energy capacity that is maintained online for you to consume during the single highest consumption hours, and then distribution and transmission capacity likewise are also driven by peaks. The size of the wire is dominated entirely by the highest capacity that needs to flow through that. And if you don't contribute to those peaks, you're really not contributing to those costs because they don't have to scale up that equipment and they're already paying to maintain it. So the cost of the utility of flowing more power through their wires during the off-peak is almost effectively zero. And a lot of progressive tariff structures indicate that by offering much, much lower costs for your transmission distribution during the off-peak. So by being intelligent, we can avoid the vast majority actually of the capacity, distribution, and transmission costs. Now the last block that we're left with is taxes. And as you know, the saying goes, death and taxes, the two unavoidable things. There's really nothing we can do by being smart load for avoiding taxes. So those come over at the full rate for our systems. Now, one thing that's important to note here is that because we're being smart about how we're consuming and because electricity costs are really predominantly driven by peaks, we can achieve a cost of power with our systems that's about 1/3 of the average cost if you were consuming naively as just a flat base load source of energy consumption. Another thing that's important for us as a company is that the amount of taxes levied on electricity are very, very important for our business model and for our ability to economically offer electrification to potential customers. So for a typical load, the taxes make up a relatively small amount people don't worry about them. But for us, it's almost 40% of the price of power we pay is dominated by taxes. And that's something that we're very sensitive to as a company. And one of the things that we've been looking at is how laying heavier taxes on electricity versus alternative or conventional fuel sources such as fossil fuels might have a negative impact on state goals towards electrification and reducing emissions. If electricity is being taxed at a higher rate than fuel oil, natural gas, et cetera, that's sending really the opposite signals that we want to be sending to consumers, because electricity overall is and is going to increasingly be the cleaner fuel source. So that's something that we're watching in the various dockets in the Northeast and New York and various states in New England. And then finally, as I mentioned, the Northeast has costly fossil fuels. So just natural gas on average is about 2 times the national average cost per unit energy. This is because we're kind of at the end of the distribution system. Most of the gas is being produced in the Midwest, Texas, and then being pushed out to the Northeast, and kind of being the last consumer on the end of the pipeline means you're paying higher costs. So the national average for a large consumer for delivered natural gas is about $4 per million BTU. In New York and New England, the EIA reports that the average price is about $7.50. So there's a lot more benefit for electrifying because of these higher fuel costs. And as I mentioned previously, we're really initially focused primarily on the delivered fuels market. And if you are in a rural part of the state, you could be paying a much, much higher rate because of the cost of actually trucking fuel to your facility. The highest I've seen at a large facility is about $18 per million BTU, but really anything in between there, depending on where you are and what system you have, is pretty typical because of that higher added cost of just trucking massive amounts of fuel to large facilities. So any oil, compressed natural gas, propane is going to have a steep premium compared to what the national average price of energy is. So these 3 reasons together are really why we're focusing on this market in the Northeast. We see it as, again, a really small, narrowly defined initial market, but really the best place to get our feet wet and really learn how to drive down our costs and how to offer our product. As I mentioned, there's limited gas access in the Northeast. So this map in deep red shows the areas without any access to natural gas, and then the lighter red is where the majority of facilities do not have gas according to census data. So obviously this is anti-correlated with urban centers, but there's still quite a bit of people and economic activity that goes on in these rural regions. Collectively, we estimate that facilities spend about $10 billion in this region on either oil or propane, and we estimate that we could save them about 25% of their boiler energy costs, or $2.5 billion of collective energy savings across the region, while also reducing their emissions. Within this initial target market, major applications in this region include, of course, schools and colleges, food processors, particularly dairies we've been working with, hospitals, paper mills. A large portion of paper mills' load are met by biomass, but many of them have to use significant amounts of make-up fuel oil to make up for extra energy that they can't get from their wood scraps, lodges at ski areas, and then, of course, homes. And even though our initial focus is on larger facilities, this is a market that we're definitely looking at moving into in the near term, particularly larger multifamily apartment complexes. In addition to the areas without natural gas, we're also exploring how our solution might be applicable in areas that have gas constraints. So the areas in orange are areas with gas moratorium. So there's a couple in Massachusetts. There's one in the suburbs of Ithaca and upstate New York. The one that's been getting a lot of attention recently is around New York City, Long Island, and Westchester. Basically, in these areas, you have local governments or communities that have decided that they do not want to add additional natural gas pipelines, and the utilities are saying they cannot accommodate new load without either a reduction in gas demand or new gas pipeline capacity. And if gas pipeline capacity is off the table, we're looking at basically using our solution to relieve constraints in the natural gas network with excess capacity in the electricity network. And this makes sense for a few reasons. One, electric grids are highly underutilized. So we have to build our electric grids to accommodate the peak load plus the reserve factor. That's only going to happen, once a year. And we've oversized these systems because we built them several decades ago when we were expecting load growth to continue basically indefinitely. And that's obviously slowed and in some places reversed. And then secondly, not only are these systems overbuilt, but they are also anti-correlated. Electricity tends to peak in the summer due to air conditioning loads, and obviously the natural gas consumption peaks in the winter as a heating load. So the times when the gas system is most constrained are also times where there tends to be excess capacity on the electricity network. So we're exploring applicability of our system actually in upstate New York in this suburb of Ithaca to see if this is something that could be a competitive alternative to adding new natural gas pipelines. In addition to that, right now we're in the middle of installing our first demonstration project. We're installing a 1.3 megawatt dynamically electrified boiler system in NYSEG service territory with Wells College. Wells College is a small university located in the Finger Lakes region of upstate New York. That project, we actually just finalized the construction documents on it, and we're hoping to finish the retrofit and be producing steam in Q1 of 2020. Basically, Wells College is in a part of upstate New York that does not have access to a natural gas pipeline, and for this reason, they rely on basically a couple times a week delivery of propane to meet their campus heating needs. Right now, they spend about $280,000 a year on propane, and they have that at a relatively fixed price that changes every couple of years based on the propane market dynamics. But for the sake of this graphic, I represented it as a flat orange line. Additionally, burning this propane emits about 1,500 tons of CO2 per year, and since the college is already decarbonized in a lot of other places pretty aggressively, this represents actually 80% of the college's remaining greenhouse gas emissions. So this is really the largest lever that this school has left to reduce their emissions. Once dynamically electrified, Wells College will be able to make use of electricity when it's available at lower costs, represented by the blue line here, and then they'll unlock the savings represented by this green triangle, basically the difference between the orange line and the blue line. We are estimating, based on the past 5 years of data, that the school will be able to save about $75,000 a year on their total energy costs, accounting for the increased cost of electricity, and will reduce their emissions by 400 tons a year. That equates to about a 25% reduction to both costs and emissions. Additionally, we plan on purchasing RECs for all of the electricity used by the boiler. So this will actually, if you use the REC accounting system, look closer to a 50% reduction in the boiler emissions and a 40% reduction in campus-wide CO2 emissions from this one project. And as I mentioned, we're expecting this project to be online of Q1 of 2020, and we're expecting that to have an attractive payback period on the order of 4 years. Now, Wells College, like a lot of the places that we have been talking with that are interested in our service, don't necessarily have the capital available to do a retrofit project and invest in a second boiler available. So to do that, we have been borrowing from lessons in the rooftop solar industry and looking at how to finance this. And what we've been offering for most of the people we've been talking with are steam purchase agreements, where basically we would partner with a financier to pay the upfront cost of that boiler and having that boiler installed in a facility. Our company would provide software dispatching that enables that system to work effectively. And then the shared savings from the dynamically electrified system would be used to cover both the cost of financing that retrofit as well as the software. So in this chart, you can see that before the agreement, the facility would have a certain cost of energy. Once the agreement is online, the savings will be split between the customer, who sees a lower total cost, and then the financing and the software, but the majority of the savings are going to the financier. Then after the agreement, the electric boilers have very long life. The customer will receive the majority of the financial savings and can continue to contract with us for software if they desire to do so. We found this is what most of the people we've talked to are more interested in, to avoid that upfront capital cost and see a project that from their perspective is cash flow positive from day one. However, for larger facilities that are very well capitalized, we can also offer just our software as a service, and the customer can of course pay for their own boiler retrofit. We call this the BYOB, the bring your own boiler model. The customer would pay the upfront cost of acquiring an electric boiler and installing that. They would keep more of the savings initially because they are bearing that cost of financing, and we could also just contract with them to provide software dispatching services. In closing, I just want to say that electrification of thermal loads is going to be necessary to achieve decarbonize in the energy sector. And one of the things I think is really important to point out about our system is that it allows facilities to decarbonize in step with the grid. So as more renewable electricity is added to the grid, the system will naturally optimize to make more and more use of electricity and will therefore decarbonize as more renewables are being deployed. So we see this really as a great way for a facility to transition. And ultimately, once it makes sense to completely electrify, that hardware is already in place and appropriate for it. So we see this as a great solution for facilities to right now invest in an opportunity that's going to have an attractive financial savings, take a big dent out of their carbon emissions, but then continue to improve over time as the grid improves. So my team and I believe that we can tackle both the problems on the thermal side while also providing a valuable service to renewable generators that are really right now looking for new markets. So with that, thank you for your time, and I'll be happy to take your questions. And yes, we have a question coming in right now already. Yes, we'll be happy to share this presentation with the group, and if anyone is interested in applicability for their facility or a facility they know of, I love doing site visits. I don't want to say that we are a silver bullet, so we only work in certain types of applications. But in those facilities where we are a good fit, I think the fit is really strong. And I'd be happy to come and look at a facility and see together if it might make sense to partner. And I can also, if anyone is interested in getting more information on the demonstration project with Wells College, I can have my contact information shared. And if someone is interested in getting some of the results from that early next year, I'd be happy to send those along as well. Do we have any other questions at this time?
So just to confirm, Jordan, thanks so much. We will be posting this webinar recording on our Basecamp site, and I'll send out the link to that once we have that ready to go, along with Jordan's contact information and the Medley Thermal website, just so everybody has all the information they need if they want to follow up with Jordan and Medley Thermal directly. Oh, we just got a question, Jordan, looking at international applications. I don't know if that's something you want to speak to for a bit.
Yeah, I'd be happy to. So we're actually working right now looking at some projects in Africa on a longer time horizon. Our initial target market, like I said, is the Northeast, but we do see applicability beyond that. I would be happy to follow up with you specifically, but I'll talk a little bit about what we're looking at elsewhere. But in a lot of applications, you have facilities that are processing raw materials and rely entirely on delivered fuels for both their renewable, or for both their electricity generation and their thermal generation. Facilities like that make a lot of sense for on-site wind and solar because their electricity costs of having delivered diesel fuel through a generator that's not very efficient, their electricity cost is very, very high. So distributed wind and solar make a ton of sense in these applications. From speaking to developers of those renewable generators, though, they see that they would like to oversize their renewable capacity, but they're worried about running into periods of curtailment. Basically, if you co-located renewable generation with this, you could oversize your on-site renewable generation. And anytime you happen to have excess, you could get some lower amount of financial value by moving that to your thermal market and offsetting some of the diesel fuel that you would be burning there. A lot of the costs actually with this, because the capital costs of the equipment are quite low, is in labor. So I think that an application for a large facility in Africa is a possibility. That said, we haven't followed up too strongly there yet, simply because we don't want to be pulled in too many directions, but I'd be happy to talk about the application here. Yes, we have a great question about if this option grows, is there enough capacity on the grid to meet the high demand for electric boilers? And then what about the capacity to the facility? Yes, so this is great. This is something that we've been looking at, and we see, you know, if we are aggressive, this could actually become a significant amount of the load on a system. So in one sense, the total amount of thermal energy being used is roughly equivalent to the amount of electricity generated, the same order of magnitude. So if you were to dynamically electrify all thermal systems, that would require a massive increase in electricity generation capacity. Fortunately, though, that's something that a lot of public policy is already looking at, with trying to turn over to a more renewable grid. So, I mean, it's a little bit of a, it's a very good question, but at a certain point, yes, if you were to dynamically electrify all of the grid, you would need more generation capacity than is available now, but there's quite a bit of excess available. And I'm not sure if there's a discrete point where it changes. It's really dependent on the local site and the local conditions. From a transmission standpoint, though, the fact that I like to throw around is there's about a 30% average use factor on the existing distribution system among the joint utilities in New York. So of the major, I just want to repeat that to make sure it's clear, of the major utilities operating in New York, their ratings for their systems versus their average load are more than three times what their average load is, which means there's a lot of already wires in place for moving electricity around if you don't contribute to peaks. And that's where having a system that has this sort of backup is really able to cut costs for the electric utility. We've been working with a few. Nikki mentioned that we were recently speaking with the Innovation Day with Avangrid, and they're very interested as a way to increase the efficiency and the utilization of their system. And then similarly, what about the capacity at the facility level? That can be one of the other cost drivers, second to the boiler, in some cases greater than the cost of the boiler. But there are a few things that we can do to mitigate that. So for one, the electric boilers connect directly at high voltages, primary distribution, even sub-transmission voltages, which really cuts down the cost of connecting. So you would still need to maybe do that last 100 feet of connection between yourself and the utility pole, but you don't really need any transformers between you and there, because you can connect at the high voltage. And while you would have to build out the last 100 feet, the real goal is to make use of the system that's already there, and there's quite a bit of capacity to do that. And if you really are limited, we can always downsize a system to only account for partial load. So we can size the available capacity. I hope that answers that question. Is our software compatible with peak, off-peak electricity pricing and battery storage? So yes, peak, off-peak pricing is a very important cost driver for what we're doing. That's part of when I went through, I'll pull up the slide once again. If I can find it, yeah. So tariffs and contractual constraints. The electricity tariff is a pretty complex, dense document, but basically we distill the important aspects of that, convert it basically into an algebraic formula that is temporally based, and that is taken into account in the optimization. In terms of battery storage, we have not yet worked with a battery storage system. I'd have to think about how that would change our system, but fundamentally I don't see any reason why that would be an issue, and we'd be happy to take a look at a system with someone if that was something that might be of interest. I think that's all the questions I had. Thank you for submitting those. Those are very good questions. I'm happy to take a couple more if people want to continue the conversation.
Sure. Jordan, thanks again. This is Nikki. This has been really informational, and is a really interesting sort of extension of some of the core thermal issues that our members tend to be focused on. So hopefully everybody enjoyed it as much as I did. I know everybody's got a real busy schedule, and we're certainly not wanting to sort of extend time inadvertently. So I would say we could go ahead and wrap up at this point.
I keep overshooting it. I apologize. My email, I'll put it into the chat right now. I was trying to pull up the last slide that has my email. So if anyone would like to continue a conversation offline, they have it. But that's just jordan@medleythermal.com. And I'll put that into the chat as well so that people can reach out if they're interested in learning more. Be happy to continue the conversation.
Great. And then we will, once again, just make sure that the webinar recording is uploaded and distributed on our Basecamp site along with Jordan's contact information. But we're very excited to have him at Medley Thermal as a friend of the RTA, and certainly would encourage you within your networks, if there are potential conversations to be made, we would encourage you to share the work that the company is doing and help put others in touch with Jordan. And want to wish everybody a happy Thanksgiving next week, and thank you for joining us on your lunch hour today.
Thanks, everyone.
Okay, so I am going to stop the recording and take our Zoom platform and close that. Once again, thank you everyone for your participation. Have a great rest of your afternoon.